Hello everyone. Let's start with the solution of this question. Okay, this is a question from KROTOV. It says there is a vertically insulated cylinder. So, what do we mean by insulated cylinder? It actually means that if you consider the cylinder to be as a system, then Q has to be zero. Heat exchange is going to be zero. Okay. Now let's start by what we are given in the question. We are given that the cylinder has n moles of an ideal gas, okay, and under a weightless piston. So initially the weight of the piston is zero. I mean, initially what the weight of the piston is going to be zero. So let the initial temperature when the mass wasn't there, we can write this that P. All right, wait for a second. Let P naught be the external pressure. Okay, so we can write P naught into V equals to N R into T initial. Okay, and once the mass has been kept, okay, so we can write the final equilibrium condition. So what will be the final equilibrium condition? Let this be equation 1. All right, and the final equilibrium condition is going to be P naught, that is external pressure, plus pressure due to that mass, that is going to be weight by area, okay, into volume final will be V minus H into S. You see that the piston is you know uh, down with a height H, okay, and that is going to be um, N R into T final. This is going to be equation number 2. Now, what we need to understand that first of all, we have to consider this process to be quasi-static process. Okay, I mean, actually, this is a very slow process. So, I mean, what I mean to say that every point, if you exclude the external mass, P internal has to be equals to P external. Okay, this is the assumption that we are taking for this question because this is necessary. Either if we consider this to be an irreversible process, I mean, this is going to be very complex and we won't be getting the solution. Okay, so what will be the net work done? That will be work done on the gas. The net work done on the gas will be work done due to the external mass, okay, plus work done due to external pressure plus work done due to internal pressure. Okay. So our assumption for this question is that the external pressure and internal pressure at every point, okay, will be same. So by this what we can see that external pressure will be acting in this direction and internal pressure will be acting in this direction. Let this be the piston, okay. So if you take the net summation of the work produced by these two pressures, this is gonna be zero. So this and this will eventually cancel out and will give the net summation to be zero. So what we are more concerned is that what is the work done due to this external mass, and that is nothing but force into displacement, that is equals to mg h. Okay, I think up till here I am very clear. The net work done. Now, by first law of thermodynamics, okay, we can clearly say that Q equals to W plus delta U. Now, Q is 0. Okay, so whatever will be the work done, that will actually bring the change in internal energy only. And the work done here is mgh, and that is equals to change in internal energy. And change in internal energy is NCV into T final minus T initial. Okay, hold on. T initial, and that is what? That is actually N It is given that we have a monatomic gas, so we'll take it to be 3 by 2 R into T final, what we are eager enough to find out, and we're left with T initial. Alright. Now what is T final? So let's come here. Okay. So from T, so hold on for a second. T final minus T initial. Alright. So from here, you can calculate T initial in terms of known values, right? P naught V by NR. Okay. So here in T initial, we can keep by P naught V by NR. Okay. And now everything is known here. Okay. So what you have to do is rearrange and find the value of TF. That is the solution to this question. Now I leave the calculation part up to you guys. Thank you so much.